Cool. Hi everyone, my name is Ryan Wisnesky, and this is a talk about theory for the working database programmer. We're taking a historical approach. This is a recording of the Texas Data Day talk that I gave earlier this year, but which was not recorded. And with that in mind, I'll jump right in. So the goal here is to describe seminal database systems, so database systems that everyone in the audience is hopefully familiar with, but to describe how they actually came about, and the idea being to improve the computer science fundamentals of the audience. And so I'll be drawing connections to category theory, to functional programming, to database theory, to entire areas of mathematics, in describing these systems. And the systems that we'll be talking about are generally regarded as forming the core of the field. They're relational algebra, which people may be familiar with from SQL-based systems, structural recursion, comprehensions, and something called the Lambda calculus. And then I'll conclude by describing some ongoing research in the graph query language community. This is work that we're doing with Marco Rodriguez and Josh Chenavier that is not covered in these other case studies. So anyway, let's get started. These slides are also available here at the URL that you see, wisnesky.net/dataday.pdf. So what will this look like? For each of these systems, we'll talk about the history, the problems that led to it coming into existence, what it is, give a definition of it, talk about an example, describe conclusions, the kind of the takeaways about the utility of the system. But the idea here is for people to draw their own conclusions rather than just be told those of the community. And then, of course, we'll describe how it's applied today. So we got good questions during the original version of this talk, but since this is a recording, I'll just do my best to try and mention frequently asked ones. So anyway, I'll jump into the first case study, but in case anyone's curious about me or why I'm qualified to give this talk. So I learned this database theory stuff over at IBM Almaden, and then extended it in my career at grad school. And now we're using it in the CQL query language over at Conexus that I'll also talk about at the end. So that's me, and if you like the material in this talk, please do consider going to grad school, as this is when typically most people encounter this type of material. All right, so relational algebra. This is almost pre-computer, I suppose, depending on your definition of computer, but the history is like this. So Tarski, which people may be familiar with as a famous logician, actually invented the relational model in a footnote in a graduate textbook on algebraic logic. The year was 1959, and I'm not sure when the transistor was invented, but this was definitely before computers were really used, or before there was an impetus to sort of take that idea further. But that impetus came 10 years later, in 1969, when Ted Codd over at IBM in San Jose rediscovered the relational model from scratch. And so he was a computer scientist working on large shared data banks and whatnot. Originally, the reaction there was allowed nothing, right? That Codd's idea of the relational model, and we'll define what that is in a bit, it was seen as an intellectual curiosity at best, and at worst is undermining existing products. So Codd then published the work outside of IBM, where it then took another 7 years or so for it to really gain traction. So Oracle came about 1977. It was based on the relational model. Around that time, when the benefit starts becoming apparent and when the research has been fleshed out about how to make it work, a whole bunch of companies start popping up and selling data management systems. So Codd wins the Turing Award in 1981. IBM DB2 launches 6 years after Oracle is founded and brings in billions of dollars of revenue for them. and then SQL, which is not entirely relational, but a widely deployed variant of the relational model, of course, runs civilization. And so this was a great success story. Started in a footnote, published to loud nothing for 10 years, and then all of a sudden Turing awards and billions of dollars in revenue and utility and all of that. So what is the relational model, and why did it gain so much traction, and even why was it so silently received for the first 10 years of its life? Well, let's give some definitions. So hopefully this is familiar to people from SQL, the structured query language, which was invented around the same time all of these things were getting off the ground in the 70s. But anyway, what is a relational database schema consist of? So it's a set of relation names, table names, and then the number of columns they have, or perhaps the data types of the columns. For the purposes of this talk, we're going to simplify things and just talk about numbers of columns. So we might say, for example, that you have a schema of friends and parents. Friends has arity 2, and parents has arity 3. So you can think table with 2 columns called friend, table with 3 columns called parent. A database instance on a particular schema, so your data always lives on a schema in a relational model, consists of a set D, which we're going to call the domain, or if you had multiple types sitting around, you might have string and integer and bool. We're just going to have one big one called the domain. And then for each relation name of arity n, so having n columns, the database instance consists of an NRA relation on D, so actual tuples of length n. So if we take our domain to be all strings, then we might have a friend relation that has one tuple, Alice and Bob, another one, Bob and Charlie, indicating that Alice is Bob's friend and Bob is Charlie's friend, and then a parents tuple. Here we have Bob, his parents are Daniel and Ellen. So of course there's lots and lots and lots of databases that could live on this schema. This is a particular made-up one. But that's really all there is to the relational model, just relations. In fact, there's even something called a binary relational model where you just have binary relations. You can get even more succinct. But anyway, the point of the model isn't so much just to say what data is, but to also describe operations you can do on the data, in particular to describe queries that you can run on the data. And so the relational algebra is a set of 5 operations that can be done to the relations on a database, resulting in a new relation of arbitrary arity. They're known as select, project, product, union, and difference. Now, there are other bases of these operations. For example, you might hear join, union, and difference, or you might have intersection thrown in there, what have you. This particular choice of operations, select, project, product, union, difference, happens to be the one we'll use for this talk, but there are many others. And the crux of this point, or the key insight into what enables the relational algebra to work, or work the way that it does, is that this set of operations that may seem like it's pulled out of nowhere, right? Just why difference? Why union? Why not some other things, right? The reason that those are chosen, and this is why what Cod showed back in the day, is that those operations are equivalent to a fragment of first-order logic called the domain-independent fragment. And so we'll speak briefly to what this is. Here's an example, since we don't want to get drawn too much into the formalism. So take this query here. It is a domain-independent query. It says, give me those tuples x and z for which there exists some y, such that x is friends with y and y is friends with z. So it's basically saying join your friend relation. So here in our example, Alice and Bob and Charlie would join, and we return Alice and Charlie. So they call this domain independent because the result of evaluating this query depends on only what's in the tables, right? We can scan the friends table to answer this query. We did not have to enumerate all of the strings that exist to answer this query. So an example of a not domain independent one where you would have to enumerate all the strings to answer it is this. Give me all of the strings x and z such that x is not friends with z, right? And so that is not something that can be answered by looking at your database, right? It can't tell you who's not in it. It depends on your domain of discourse. And so this query is called not domain independent. And what Cod noticed is that the relational algebra is exactly that set, is equivalent to those domain independent first order logic queries. And that's called Cod's theorem. And my claim is that relational algebra and its practicalization, SQL, succeeded precisely because they are first order logic, modulo that caveat about domain independence or not. And I would argue that the reason we see SQL adopted is because of the unusual effectiveness of logic within information technology systems. And so I'm of the opinion that relational algebra will outlive myself for sure. And it's quite a marvel of the human mind and nature and all of that. So anyway, to conclude this story, what are some of the key theoretical results about this model? So why is this model nice? So one of the things is that query evaluation is polynomial time. So if you fix a query, then the rate at which the running time of your query scales relative to the input data is polynomial. So that means it's tractable in practice, although database management systems have to go to heroic efforts to actually realize that. There is that nice theoretical result. Similarly, for certain fragments of relational algebra, so the select, project, product fragment, equivalence of those queries is exponential, or rather NP hard, but it is decidable. And since queries tend to be small relative to data, that result there is what drives many relational query optimizers. In particular, their minimization and composition or view unfolding algorithms. They typically end up using techniques like B-trees and hash tables and stuff to make all that go faster. So much to be admired in the relational model. A little bit less to be admired in some of its practical realizations. Or rather, if you look at SQL, for example, it's based on relational algebra, but uses a 3-valued logic. It allows you to write null as a data value. And so you run it against circumstances in SQL which are unintuitive, such as null equals null not being true, but being unknown. And so in practice, things get, or the difference between theory and practice is greater in practice than in theory, I guess you could say. But anyway, we all know and love SQL. Finally, one caveat I alluded to before, but definitely should mention now, is that why not just use first-order logic as a query language? And that's that checking if a first-order logic formula is domain independent is actually undecidable. And so there are syntactic restrictions you can put on first-order logic to stay in that fragment. But another reason relational algebra succeeded, I would say, is because it precisely codifies that undecidable fragment of logic. Cool. So that is the relational algebra. Ordinarily, I would pause here and take questions, but we can just move on. And so in between each of these descriptions of these seminal systems, I've placed a little historical interlude about what was happening between it and the next big thing. So here, the relational model was popularized in the late 70s, and its killer app was essentially replacing the graph and network-based data models from the previous decade, right? It was simply more effective at giving things like logical data independence than those were. And so a huge industry arose, just moving everything over into relations. And so that worked well for a while, but then, of course, people were finding that relations themselves were not expressive enough as a formalism to encode some of the computations they wanted. And so there was a Cambrian explosion of other data models starting in the 80s and into the 90s. So you've got your object-oriented databases, your object-relational databases. Datalog came around, definitely a golden age of database research. And so researchers found, though, that the relational algebra was insufficient for these new types of systems. And so nowadays, of course, SQL still gets extended all the time, but you often hear about relational algebra as more of a gold standard upon which other systems can be compared, such as the other three systems we'll be talking about in the rest of the talk. So, structural recursion. This is the next system, and I use the word system lightly because like the relational model, there are many implementations of this idea, right? Just like Oracle implements the relational model, IBM does. Many systems will implement structural recursion. But what does it look like in the history? So the first known instance of someone actually calling out primitive recursion as a definition mechanism, and this is what it is. It's a mechanism to allow us to define functions, and for reasons that I'll get into later, I'll probably inadvertently say structural and primitive interchangeably in this part of the talk. But anyway, it was a mathematician called Dedekind who used structural recursion in 1888. So this was back when mathematicians were becoming more rigorous in how they were actually defining the things that they were talking about. And then, of course, logicians used it quite heavily. So Skolem in 1923 invented something, or discovered something called primitive recursive arithmetic. And people may have heard about piano arithmetic, for example, which is another axiomatization of arithmetic. But the one that Skolem invented was shown 20 years later by Haskell-Curry to not require logical quantifiers, just equations. And so what that means is that starting around the 1940s, there's this connection between things that are equationally defined and things which are recursively defined. And then starting in the 70s, around the same time SQL was getting popular, computer scientists in the programming language community realized that structural recursion is a principle that could guide the design of abstract data types, things like lists and queues and stacks and these types of things. So that community does that and is a great success. So then finally, around the 90s, researchers with feet in both communities notice that there's structural recursion is happening both at the logical level to deal with data, like how Skolem and such were using it, and dealing with data types, like how programming language people were dealing with it. And so structural recursion becomes essentially a standard for implementing mixed programming and database systems that require more expressive power than relational algebra has. So that was a bit of a mouthful, but I guess the point here is that the same idea of using recursion in programming languages and in query languages originated in both communities and was synthesized together in the 90s, and now you see structural recursion used as a query language and as an implementation technique pretty much everywhere. So in particular, there's something called the iterator model of SQL query evaluation that became popular in 1994 and is now, you open a textbook and that's what it's describing, is this structurally recursive way to implement a database, which let's talk about now. So structural recursion, what is it? Well, it's related to something called structural induction in the same way that catabolism and anabolism are related. One is about building things up, the other is about processing things down. So an inductively defined set builds the elements in the set in terms of the other elements in a well-founded way. So basically, this is easiest to understand by an example. And it's really the natural numbers that kind of spurred the development of recursion to begin with. So the set of natural numbers is inductively defined, right? 1 is a natural number, that's the base case. And then we say if n is a natural number, then so is n plus 1. That's the inductive step. And then we say the natural numbers is the smallest set satisfying those two properties I just gave. That's what it means to say the natural numbers are inductively defined. And the reason that's useful is that means we can then process them by breaking them down, right? So how would we define multiplication by 9? So, well, we have to say the base case, so 1 times 9 is 9. Then we have to say the inductive step, right? So n plus 1 times 9 is n plus n times 9. And that we've just defined multiplication by 9. There's exactly one function from the natural numbers to the natural numbers that satisfies these clauses. It's called the induction principle, or excuse me, one function called multiplication by 9 satisfying these, and then the proof principle associated with the natural numbers says that if we want to prove something about the natural numbers, just prove that it's true about the number 1, and that if some property is true of n, that it's also true of n plus 1. So that means we can prove, for example, that multiplication by 9 is commutative by doing induction over the natural numbers or what have you. Anyway, the point of this isn't to really get into what induction is mathematically. It's more to show how it comes up in data processing. So here, by far the most common example is a list, right? So in data processing, a list of t, like a list of strings or a list of int, I mean, that comes up pretty much everywhere, right? Even a database table is ultimately, you know, it's a set of rows, but they're represented as a list somewhere, you know, on your screen in Excel, right? Or, you know, it's kind of a list because they're laid out on disk in physical space, and so there's an order or what have you. So lists, at the very least, underlie a lot of data structures. And so they're inductively defined like this. We're going to define lists of integers. There's a base case, the empty list, called nil. And then a list, a non-empty list, is just the cons of an integer in an integer list. So cons is just the concatenation that abbreviates it. So it's taken an integer and appended onto an integer list. And so because lists are inductively defined like that, right, you get for free, or rather the math says there always exists a unique function to process them called structural recursion. It's usually called fold in programming languages, just because that's shorter to write. And what does that do? Well, it says if you have a replacement for nil of any type, say a, and a replacement for the cons operation, you know, that does appending, that you can recursively process a list, right? So when you hit the nil, you replace it with your value, and when you hit a cons, you recursively apply the fold operation to the rest of the list, and then you apply the function you gave fold to that result. So the example of this is actually summation. So if you fold 0 and plus through a list, that sums them up, right? So for example, suppose you had this list, cons 5, cons 7, cons 9, nil, right? You replace nil with 0, and you replace cons with plus, and now we have 5 plus 7 plus 9 plus 0. And we've just summed the list, right? And as you might imagine, that kind of processing over lists happens all the time. In fact, you can prove that that iteration is universal, that there's nothing you can't compute not in that manner, at least if your language supports things like products and some stuff like that. So anyway, why is that cool? Well, that's cool because on the one hand, since lists can encode things such as sets or bags or other data structures, we can implement, for example, a relational algebra using them. And so now, how do you generalize the relational algebra? You just drop down into the implementation layer and process lists. And that's indeed how people got more expressive power out of relational systems. One caveat to that, of course, is that you have to be careful when you're doing that because your lists are encoding other data structures. And so if your other data structure says things like no repetition, then you have to make sure that you preserve that when you process the list. And that actually led to the next research that we're going to talk about next. But for now, we'll finish with structural recursion. And so why else is it so well adopted now, in addition to that property I just mentioned, that it's expressive? Well, it's also easy to optimize. So for example, if you iterate through a list twice, there's a theorem that says you can just iterate through the list once. It's called fold fusion, or pipelining from the more data side. And so there's a powerful theory of optimization that people like. Also, most algorithms just straight up are what's called primitive recursive. This is a result from a long time ago, and it turns out that primitive and structural recursion are equivalent. So in almost all circumstances, if you have an algorithm that almost terminates, it will be structurally recursive over some data structure. And so this is pretty close to as expressive as things come. However, it is dangerous in the sense that you're programming at such a low level, right? You're programming right at the level of lists. And so as a user-facing programming language, it's less than ideal. And that is where we're going to go next. So pause, ask for questions. But since this is a recording, there are none. And so on to the next subject. So the next subject is comprehension notation, which provides a user-facing query language for the structural recursion so that we can write things that look more like queries than things that look more like programs. You know, which is not to say programming isn't a great way to interact with a database, just that sort of the point of database theory is to have query languages rather than programming interfaces. So comprehensions are a user-facing query interface that goes back a long time. It actually goes back to 1901 and Russell's paradox. So this is comprehension notation here. It says, let's define a set R. It is a set of all x's such that x is not a member of x. So it's a set of all sets that do not contain themselves. And so what we're doing here is we're doing a comprehension, right? An unrestricted comprehension. All sets, we're comprehending through all sets according to some predicate, in this case that x is not a member of x. So unfortunately, as a logical principle, that is unsound because it leads to the conclusion that the set R is a member of itself if and only if it is not a member of itself, from which in most logics you can then conclude that 1 equals 2 and the moon is made of green cheese and all of that stuff. Unfortunately, or this was unfortunate in the sense that mathematicians and computer scientists really like comprehension notation because it's such a nice or an easy and declarative way to say things, right? You just say a property that you want things to share and off you go. So after much wrangling and head scratching, mathematicians eventually moved to something called bounded comprehension notation. And so ZFC set theory, for example, that is used even to this day, is based on bounded comprehension. And so what that means is just, you can never say, give me all sets such that. You can only say, give me all sets such that, and also that are in some other set. So it's basically a way to avoid talking about all sets at once. However, for the purposes of this talk, what is more interesting is not so much how they fixed unrestricted comprehension back in the day, what is useful for this talk is that something that shows up as a query language called do notation is a generalization of bounded comprehension. And so this went more towards the using the fix that they discovered in ZFC set theory. However, they did eventually fix the unbounded comprehension version, believe it or not. So there's something called a topos in category theory that allows you to do that type of unrestricted comprehension. But it's orthogonal to what we're talking about here. So anyway, right, where does the history, or what else do I want to say about the history? So comprehension notation, as I'm describing it now, is bounded. The originators were, in this case, Mogi back in the 80s, and then folks in functional programming such as Simon Peyton-Jones and Phil Wadler connected this notation to input-output, which is quite a shock, right? You wouldn't necessarily think there's a connection between set comprehension and input-output in the sense of write string or fire missiles, but there is, and that was actually fundamentally related to the development of a programming language called Haskell. And then this, Wong and Tannen and some other database theorists also proposed comprehension notation directly as a query language, which is what we'll see in this talk. So let's give some examples of comprehensions. What are they? So let S be the set of integers, and here's a comprehension. It says, give me the set of A's plus B's such that A is in S and B is in S and A is not equal to B. So what does that do? Well, that traverses the set S twice and returns a set containing the sum of all the non-equal elements. So if S in this case was 2, 3, then the sum of 2 and 3 is 5, right? So it tries 2 and 2, doesn't do that because they're the same. 2 and 3, it adds that. 3 and 2 adds that, but we're a set, so it only adds it once, and then 3 and 3 are the same. So we just end up with a singleton set of 5. And that's basically all there is to it with a comprehension. The thing to notice is that these are bounded comprehensions, right? We're saying all A in the set S of integers, all B in the set S of integers. We don't just say all A's, period. That's really the only difference between bounded and unbounded comprehension. And key fact, this comprehension notation can be implemented using a set of database-like primitives, right? So in particular, there's an algebraic formulation of this calculus. So we say comprehension notation is a calculus because we're talking about bound variables, right? A and B here are variables. Down here, here's the set of operations you need to have an algebraic formulation. So the claim is this: you can implement bounded comprehension notation through sets using the following 6 primitives. Map, which means if you give it a function from A to B in a set of A's, it gives you a set of B's by applying the function you give it to each thing in your set. Map the function through the set. Filter, you give it a predicate and a set, and it just returns the one that matched the predicate. The empty set, you have to be able to form a singleton set and unions of arbitrary sets of sets. And then finally, if I give you an A and a set of B, you have to be able to pair up that A with all the elements in the set to give me a set of pairs. If you can do those 6 things, then you can implement bounded comprehension notation. And in fact, nowadays, databases implement those 6 things and expose comprehension notation as a query language. And that is the claim, that comprehension notation succeeded as a query language precisely because it is the same mathematical notation that everyone else in the world is using. And so what does that notation buy you? What are the key theoretical results? So there's a normal form for comprehension notations. If you have a bunch of comprehensions, you can always flatten them into one. That's the basis for many query optimization techniques. There's a translation, of course, from the comprehensions into structural recursion. I may not have mentioned that before now, but that's actually a key property, right? That these user-facing languages can then be implemented with structural recursion that we saw from before. And then finally, another key property here is that this notation, it works over multiple collection types, right? So you can do comprehension through sets, comprehensions through bags, comprehensions through lists, and more generally. Now, out of the box, there are some limitations about, it can't do aggregation, there's no joining, that type of stuff, but there's research available that obviates most of those objections. And in fact, we find that comprehensions are implemented in Python and Java and Haskell under the hood in data integration systems like IBM's Hill, Microsoft's Rondo. And in fact, the final thing we'll be talking about is where this led, which was now that we have this notion of comprehension notation that desugars into structural recursion that is sufficient to encode relational algebra, how do we marry it to a general purpose programming language in the guise of Lambda calculus? And so the Lambda calculus is the next bit. And then that whole story, relational algebra, structural recursion, comprehensions, Lambda calculus, is what you might call the main body of study in programming or database query language, the field or what have you. Anyway, it's a key part of the literature in that it tells a complete story that is still the state of the art. So what's the history of the lambda calculus? So it was invented before computers, so I wanted to say it's a model of programming, except it was invented before programming existed. It was actually originally proposed as a logic. So Alonzo Church proposed that back in 1932. 3 years later, it's shown that it's inconsistent by one of his students. And so he isolates the portion that's more relevant to computation, and that's when the untyped lambda calculus was born in 1936. 1940, Church discovers a weaker but logically consistent fragment of his calculus that's called the simply typed lambda calculus. Both the untyped and simply typed versions are still in use today. It took another 30 years before someone was able to actually come up with a model of the untyped lambda calculus. And by that I mean come up with a mathematical description of this calculus that wasn't actually in terms of the syntax of the calculus. With that in place, this whole field evolved rapidly. So because lambda calculus is based on programming, around this time, like 1980 or so, that computers are going mainstream and such, these calculi get extended and refined. So dependent type theory comes about. Haskell shows up in 1990, and then it pretty much took over. Like it's rare to find a language nowadays that doesn't have lambda calculus as an underpinning, just because most programming languages can talk about substitution as part of how they compute, and so there's a direct connection there. But for the purposes of this talk, our goal is to take the data model stuff we were talking about and embed it in the lambda calculus so that we can talk to databases as we're doing our programming. And in service of that, in this talk, we'll be using the untyped lambda calculus because there's less to write. But it's the typed versions that are actually mathematically easier to understand. And so I don't want to get too much into the details of what lambda calculi are. There are plenty of introductions and tutorials, but basically there's a thing called a term. So we have lambda terms, and that's what lambda calculus study. And terms are either variables, we'll write as x or y, or they're an application of a term to another term, which is written juxtaposition, or there's an abstraction of a term over a variable. So that's written lambda x.f, and that's supposed to indicate a function f of one input x, and so the variable x can appear in the body of f. One thing to keep in mind, of course, is that variables, they're just placeholders. So the function lambda x.x indicating the identity function is the same as the function lambda y.y indicating the identity function, because they just differ in the names of their variables. Anyway, there's a single equation called beta reduction that is sort of the point of the lambda calculus. It says if you have an abstraction, lambda x.f applied to g, that is equal to substituting in g for the variable x in the body of f. And so some examples, right? Lambda x.x is the identity function, right? If you apply it to anything, it just returns that anything back. For example, if you apply it to itself, it returns itself. There's a famous function called the y combinator. It's written out like this. It has this interesting property of being a fixed point finder, that if whatever you give it as an input, you get back out as an output. So that is lambda calculus. Hopefully people can see sort of the connection to programming with variables and substitution and function application and all of that. But the key theoretical results are that, of course, the untyped lambda calculus is Turing complete. So, if you can do it on a computer, you can do it in the untyped lambda calculus. The simply typed version does not have that property, but has some other pleasing properties. Proofs can be represented as lambda terms. That was actually the original motivation, and it underlies a lot of implementation techniques, but isn't necessarily relevant to the users. Lambda calculi are also the internal languages of things called Cartesian closed categories. And so there's a sense in which lambda calculi just are substitution. they are a very natural syntactic embodiment of a semantics about substitution. And then finally, there's so many different ways to actually evaluate these lambda terms, right? You can evaluate them lazily, strictly. You can translate them into variable free form. All kinds of ways to evaluate lambda terms quickly, and that's a lot of what writing a compiler is about, is like picking an evaluation strategy and running with it. So anyway, the technique, these lambda calculi are used as underneath language integrated query systems such as Microsoft Link, Data Parallel Haskell, the monad comprehension calculus. The point really is that we take this lambda calculus, which has notions of variables and applications, and we literally just add to it these primitives here: map, filter, empty, singleton, union, tensor, right? So provided we have these in our lambda calculus, these comprehensions that we want as a user-facing programming language are also themselves implementable in the lambda calculus. And that is essentially how these systems such as Link and DPH actually work, is by embedding those comprehensions into the lambda calculus using the lambda calculus for the binding constructs of the comprehensions. Anyway, the caveat to keep in mind here is that this implementation technique works for purely functional programs, but not as much for imperative ones. And so, for example, when you have functions that fire missiles, or that may take 20 days to run before they return petabytes of data, you may not. Those have such an effect that they, just naively putting them into a lambda calculus means things like missiles fired twice, or we have to recompute gigantic computations and whatnot. So anyway, if you're in a world that has side effects, you have to be a little more clever in how you bring the query and the language together. But they are the tried and true method to getting all this stuff to work together. So with that in mind, that is the end of the story of the history. We started with relational algebra, sort of the first really formal data model. We ended with the untyped lambda calculus as being, programming language in general. And then we also talked about structural recursion as an implementation technique for comprehension notation, which is a user-facing query language that can be compiled through structural recursion all the way into the lambda calculus that we're embedding our comprehensions in. And that is the textbook way to build a database query language. So in the little bit of time remaining, I just wanted to mention some things that are current research, in particular research on graphs and categories. So graphs as a data model haven't received quite as much attention from academics as those we talked about today. They've certainly received a lot of attention, but I think the reason for this actually is that on the one hand, there's a temptation to think of graphs as special types of relations, and on the other, so making it unappealing from the relational point of view, and then from the programming language point of view, graph data structures are not inductively defined, and so the natural way to traverse them is based on stateful edge walks, like you might find in Apache Tinkerpop. And so for those reasons, it's not as easy to study graphs using the techniques I described today. However, there are some folks working on that. So Josh Chenavier is over at Uber. We formalized some work on algebraic property graphs using category theory. Marco Rodriguez is working on generalizing Apache Tinkerpop from graphs to other data structures. And then at Conexus, we have something called CQL that generalizes from graphs to categories and gives you what we would argue is the next seminal system that you will see on a list like this when history is reviewed 20, 30 years from now. So I'll conclude with some brief description about that, the next seminal system. So Whereas we've seen relational database theory, we've seen a little bit of graph theory, programming language theory. Category theory is new. I'm not really going to describe, what a definition of a category is. It's on the slides if you want to see it. But suffice it to say that it was invented 1946 to migrate theorems from one area of math to another. And so, inasmuch as we just saw that, relations are database schemas and such, we can think of category theory as being a natural language in which to describe migrating data from one schema to another. And that's the premise of what we're doing at Conexus. So in that data model, you have the best of both worlds in the sense that your schemas look like graphs. So here's a schema for employees and departments, or employees have managers. But your data looks like relations, right? Here's an employees table, right, that says employee 102's manager is 102. Looks like that's the CEO. So this categorical data model based on, or this category theoretic data model gets both aspects of the relational model and the graph model combined. And it has a nice IDE that you can go off and try and play around with, as shown in the screenshot here. Anyway, I am encouraging people to get in touch, so my email's there on the screen. Happy to chat with folks if they're interested in the Conexus CQL query language, just briefly described, or any of the other work on graphs. And other than that, for folks interested in the 4 seminal systems that were described, relational algebra, recursion, comprehensions, and Lambda calculi, there are many books, and grad school is a great option for learning more. Thank you, and it's been fun.